Let's continue our discussion about the area of a surface of revolution. Last time we derived a integral that expressed the area of a surface of revolution. And what we want to do now is we want to adjust our formula to account for the different ways the function is expressed. In other words, the situation that we looked like originally was y was equal to f of x. In other words, x was the independent variable and y was the dependent variable. But we can also write functions as x being equal to g of y. In other words, we need to get used to really y being the independent variable and x being the dependent variable. We also want to allow some freedom for our axis of rotation. So we are hoping that we can study situations such as rotating about the x-axis or rotating about the y-axis. Let's take a look at this diagram on the screen we have here. So let's compare these two pictures and let's have our axis of rotation for the diagram on the left be about the x-axis, right? And it looks like we're taking this function, right now, let's think of it as y is equal to f of x. So we're going to rotate this curve right here about the x-axis. That's the diagram on the left. So when we rotate about the x-axis, our surface area A we saw earlier was the integral of 2 pi, and then I'm going to put r ds over here. And remember, 2 pi r, that's the circumference of a circle. So we have a circle over here like this that we're rotating about the x-axis. So that's that 2 pi r right there. And the ds is going to be just a little bit of arc length that we're going to rotate around. So we rotate that little bit of arc length around, we're going to get a strip like this. Okay. Now, when we look at this r here, that's going to be the radius of this circle. That's given by the y coordinate of this point here. So when we rotate about the x-axis, y is the radius. Okay, so if I wanted to rotate about the y-axis, so let me put a loop here about the y-axis like this, and let me write about the y-axis. This is the column on the right, or the section on the right. Then I hope we can see from our picture, our circle looks like this. The 2 pi r looks like this. And the radius this time is going to be given by the x coordinate. So I'm going to put about the y-axis implies that x is the radius. Okay. So one of the things that we'll notice that the radius is always perpendicular to the axis of rotation. So this is an important idea, so I'm going to highlight this. The radius is always perpendicular to the axis of rotation. And we can see that from both of these diagrams. All right. So I also want you to notice that when I write the area formula, the area in both cases is 2 pi r ds. So this is the way I generally think about a surface integral like this. And notice how the r and the ds, these don't specify which axis we're rotating about, nor does it specify what the variable of integration is. So what I want to do in the next step is I want to break these things down to the variable level. So let's consider two different cases. The first case I want to look at is I want to look at what happens if we're in terms of x. So earlier you saw that I wrote y is equal to f of x. That means that we're working in terms of x over here, right? And when we do that, what does our formula become? Our formula becomes a is equal to the integral. We're going to have 2 pi. Remember, the radius was given by y, but in this case, y is f of x. And then the ds part, in terms of x, is just 1 plus f prime of x squared dx, right? And we want to indicate our limits of integration. So, I could put a b here, a here, and a b here, and then we're going to integrate from a to b. All right. What happens if we go about the y-axis, but we're still doing everything in terms of x? So then in that case, my area formula is going to be the integral. It's still going to be 2 pi. This time, my radius is given by x, right? So I'm just going to put an x in for the radius. And then my ds is still going to be the same as it was in the case on the left. That's going to be 1 plus f prime of x squared dx. And my x values are still going to range from a to b. So that hasn't changed. So when we're doing everything in terms of x, but we're rotating about different axes, the thing that really changes is the radius. In one case, the radius is f of x, and in the other case, the radius is x. And the key to know which one is which is to remember what we highlighted at the top here. The radius is always perpendicular to the axis of rotation. All right. So let's take a look at a different situation. Let's do this situation now in terms of y. So let me erase this label of our function, and let's change that label now to be x is equal to g of y. So in this scenario, we're going to be writing everything in terms of y. So let me put in terms of y. And when we're doing things in terms of y, my integral is I'm going to put a dy at the end because everything's going to be in terms of y. And my limits of integration, they're not going to go from a to b anymore. They're going to go from c to d, where those are the y coordinates of those two endpoints. So we can put a c here, and we put a d here like this. Okay. All right. So let's write down the integrand now. The 2 pi is always there. Remember, when we're rotating about the x-axis, y is the radius, and we're doing everything in terms of y. So this time for the radius, I'm just going to put a y. And when I go to write the ds piece, the ds piece is going to be 1 plus g prime of y quantity squared dy. All right. Let's do the other case. Let's do the case where we're going about the y-axis now. So if we're going about the y-axis and we're doing everything in terms of y, what do we get here? Well, we're going to get the integral from c to d. This is going to be 2 pi. This time I want to write in an x thing, but remember, x is our dependent variable right now. So how do we get x? X is given by g of y. So I'm going to write my g of y here like this. And I'm going to put the square root of 1 plus g prime of y quantity squared dy. Okay. So really, we have kind of four different formulas corresponding to the four different cases that we have. In terms of x, we have two formulas. We have the one about the x-axis, and we have the one about the y-axis. In terms of y, when we rotate about the x-axis, we get a new formula over here. And in terms of y, we get a new formula when we go about the y-axis like this. But I wouldn't really memorize these formulas. I would memorize this basic formula right here. And I would just figure out what r is and what ds is based on using your picture and using the fact that the axis of rotation, the radius is always perpendicular to the axis of rotation. All right. All right, everyone. We'll work on some examples in class. Take care.